I'm going to act like other people are here, even though it's just two people, just because people might watch the recording. So if I say something silly, that's why. All right. First thing we're going to do is go over the entire unit again, just a sneak preview. Also kind of review the stuff from last time. Oop, I think someone joined.
Yes.
Here we go. We got more people. Awesome. So, all right. So quick review over the stuff from last time, and then I'll also insert the new section. So this is all section 5.1. We did all of 5.1 except for 513. 513 is what we're going over today. Area of a plane. So integrals help you find the area, but this area can be used to figure out other things as well. That's the main purpose of this entire section, is you can use integration, the adding up of little bits, infinitesimally small bits, to find other things like the area between curves by just subtracting the average value of a function. So you can add up all the y values here along this purple graph and then average them out, however many there are, divided by b minus a, and then it gets you the average. This is what we're going over today. So I'm going to kind of skip over real quick to just go to what the other thing we went over was arc length. And that's just adding up all the infinitesimally small distances amongst the curve from A to B, and you get arc length. The new stuff is all about volumes. Now, if you took Calc 1 anywhere else besides Abanzi, they usually do go over this. So it should be at least partial review, but I do have some other things to add to this because improper integrals work well with it. So do pay attention if you've seen this before. Okay, this right here is the volume of a solid of revolution. And there's a formula here. Don't worry about the formulas right now. We're going to go over those later. But basically what we're doing is we're using some function, in this case this red one, and we're rotating around the x-axis in this case, and it forms a shape. This one we're rotating around the y-axis, it forms a shape. You can find the volume of the shape using this formula, which we're going to go over later. Okay, this is called washer method. Essentially, you're doing the exact same thing, only you're hollowing out whatever solid that you're forming. So this one you're forming a solid. It's like through all the way. It's pure. There's no holes or anything. This one, actually, there's a hole drilled in the center of it based on this g function. It's the same thing. It's the same equation, only you're subtracting off a part of it. Again, we're going to go over the equations in a little bit. Here is one where it's the y-axis. I did not put the equation on there, but it's the same thing as this bottom one, only with respect to y. I just didn't put it in there yet. And it's hollowed out at the center. You can see it's going around there. This other part is with cross sections. And essentially what you're doing is you can pick any shape. This example right here, a square, equilateral, triangle, semicircles. And you can imagine stacking those shapes, infinitesimally many, across this whole thing with the base of it, the base of this solid, being two functions, basically. In this case, it's the red and the blue here. It forms the base of each of these rectangles. And you could have technically infinitesimally many of them. When you do have infinitesimally many areas and you're adding another dimension to it, that's what's finding volume. Area is two-dimensional, volume's three-dimensional, and you're adding that other dimension by integrating it from 0 to whatever that intersection point is. So that's what makes it 3D. That's what makes it you can find the volume. This is squares. Again, imagine infinitely many. I'm going to show this graphic in a little bit so it'll make more sense, but when we get there, it'll make more sense. This one is equilateral triangles instead of squares. Again, imagine infinitely many. There's a volume for it. And then here's semicircles. It forms like a little dome. It looks like that. Okay, to get a visual for it, I've had students in the past make these with pieces of paper. They're usually pretty annoyed by them because a lot of them can just picture it in their head, but that's what it looks like. We're not going to worry about that so much. So to picture this, I have some visualizing volumes links here that should help. This first one is disk method. This is when you're just rotating it around, and this thing shows it. Oops, loading. This thing shows it a little bit better because you can actually see it in 3 dimensions. Now, if you notice, there are 1, 2, 3, 4 disks here. Technically speaking, there should be infinitely many, so I could always just crank this up here, and now there's way more disks here. In fact, when you do the integral, it's going to be infinitely many disks that are infinitely thin. Obviously, you can see that there is a certain thickness to this, but you can imagine infinitely thin of these, and that's basically you're adding up the area of every single one of these throughout here and figuring out the volume of this. I like to think of it as like a stack of pancakes, or if you know what a CD spindle is, if you know what a CD is, you're stacking CDs of like different radius. They have a different radius. They're smaller as you go up here, and there's a certain volume of that shape. But you have to imagine those CDs, those disks being infinitely thin. We can't make them infinitely thin here, but you get the idea. And this is kind of nice because, and this is linked on this slideshow too. So if you want to look at it, you can kind of experiment with it and like kind of visualize this whole thing in 3D. I don't know, I think that's pretty cool. This other one is washer method. This one's not as easy to work with, but essentially what I'm going to do with this one is just click revolve, and you can see it revolves. First of all, it has two functions here, and it's going to, you can move this here. You can revolve this, and you can see how it's, that inner function, that blue one, is going to be subtracted off to find the volume of the entire shape. So I kind of like to see this, so you can kind of see this part right here is being subtracted out. It's not the best visual, but it's the best thing I could find on the internet for this. But essentially what you'd be doing is finding the volume of the green and then subtracting off the volume.
That's pretty cool.
Yeah. And then the last one is probably the coolest one, so I kept this one for last. So essentially with this is you can click a square, and you can see this, there's a square here, and you can move the square wherever you want, but you have to imagine infinitely many squares along this path. So what I can do here is I can add more squares, and it fills up. Eventually it looks like it fills it up completely. Obviously it doesn't because it's only 100, but you can kind of imagine this shape has a certain volume, and all you're doing is adding up all those little areas from 0 to whatever this goes to 1. But that's essentially what you're doing here is you just need to figure out the area of one of these and then integrate it throughout the entire integral. So we're going to find the area of one of these. So just imagine there's, just imagine there's one of them, and then you're using the integral from 0 to 1 to figure that out. Now, if you notice this graph right here where my mouse is, this square is like facing you, so you can't really see it. So we are going to work on drawing these in 3 dimensions. It is not the easiest, and you might think that my drawings aren't the best, and I apologize for that, but I will do my best to draw these. This is just 2-dimensional, so you can't actually see it. So this is kind of what this looks like right here. As you can see, it's facing toward you, but if you kind of turn it, it gives you a little bit of a sense of the depth for it. Okay, and again, you can have infinitely many. That's squares. Now, if you notice, the one thing I want you to notice with the square is the base of the square is basically the distance between it is, from here to here. Okay, so if you, let's go back here, let's zoom out a little bit. It's based on whatever y value this is minus this y value here. We're going to talk about that in more detail when we actually go through a practice problem. You can have other shapes like equilateral triangles, which again are based on that base right here. And you can have infinitely many of these. Let's move this all the way over here, and then you can just have infinitely many across. Kind of a cool looking shape. And then if you do semicircles, this one's my favorite. It looks like a little like dome almost. Let's do this. And they're just semicircles, so it's just the area of a circle divided by 2. Again, you can't see them if you look like this, so we're going to be graphing like this. This is the y-axis, and this is the x-axis here. It matches with this red and this blue here. It's just tilted. So that's a main thing that we're going to be going over today, is the volume of these things and then the volume of the solids of revolution. Okay. Is there any general questions right now from anybody?
Nope, you're good.
All right, cool. All right. Let's go to the whiteboard. All right, so here is a brief rundown of what we're going over. I already did the overview. I'm going to be going over practice problems with 513 right here. We'll do some example problems along the way. Then we'll do any practice final exam stuff that you want. And then the last part is just office hours if you have them. If you did do a quiz retake, I am still grading those. It does take a while because I ended up having a lot for quiz 2. Plus all the ones from quiz 1, so it was more quizzes than I'm used to grading, so I could not get the 24-hour turnaround time for those. Things we're going over today: 513, volumes, disk method, washer method, cross sections. Kind of gave you a preview of all that already. So this is basically, we're going to be going over all of this today, and it's going to be crazy. So let's zoom in for disk method. Disk method is a method for finding volume, in which you're basically, what I said before, where you're adding up all those little CDs, the areas of the CDs throughout an entire integral. So what you can do is imagine this function right here, this red, this f of x, and imagine it being rotated around that x-axis here, and it forms a shape that looks like this. The shape that's formed, that solid, is called the solid of revolution, and you can use this equation right here to figure out the volume. Now this volume, if you're wondering where this equation comes from, it's based on the volume of a cylinder. The volume of a cylinder is pi r squared h for its formula. Okay. Well, in this case, it's not really a cylinder because a cylinder would just be like if you graphed it out. Oops. if you graphed it out, it would just be like a horizontal line like this. And say you're rotating around here, it forms that cylinder-like shape. You can kind of imagine a cylinder-like shape. Well, the radius for this is just from here to here. It's the same every time. Okay, so that's why you can just have R and it's constant. Here, the radius is not the same. If you notice this disk right here, this first one, let me do this. I'll match the color. This radius right here is from here to here. This radius right here, though, is here to here, and this one's bigger here. So the radius is changing based on this f function, okay? Because wherever the f function is, that's what the radius is. So if the radius is here, let's just say this is 2. I didn't make a function, so I don't know what value that is. The radius is 2. If the radius here is like 1, let's just say, then the radius here is 1. So long story short, the f tells you what the r is for each little bit of these radiuses. So instead of using r for the equation, sometimes it's r of x. I'm just using f of x here. Okay, if you go back to my notes, I do use r of x because sometimes you'll actually see that being used. So let's go back to my notes here. I have r of x right here. It's the same thing as f of x. It's this red function here. So whatever function is there. But again, I just wanted to show you both just in case you look somewhere else and you're going, why is he using r? My teacher's using f. It's the same thing. It defines what the radius is. So that's the r squared. This dx ends up being the h because you're just adding up all the x's along here from a to b. So that's what that h represents. So this basically means here's the pi. Pi is a constant. Remember, the integral means you're adding up all of the areas from a to b. In this case, it's going to be the areas of all these disks. So that's essentially where the equation comes from. You don't need to know where the equation comes from. It's just some people ask, and I just kind of wanted to explain that. There is a video as well linked on the website if you do want a full explanation of where this equation comes from. But it is pretty cool to basically think, oh, I know what the volume of a cylinder is. Let's just act like this thing is some crazy cylinder defined by F for the R, and then you have this new formula. I don't know. I think it's cool. So
yeah, it's much better. You know what to put in, you plug it into that equation.
Right, exactly. Plus, it's. I feel like it's easier to remember because it's just pi r squared h, which you probably remember from another class. I don't know. But all right, so let's do an example because this is still very, very complicated, and an example could help tighten the screws a little bit for this. So it says, find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. So here's a curve right here. Here's a line, and then here's another line. That's a vertical line. So what we're going to do is we're going to graph all of this to figure out the region that's bounded by all these three things here. Okay, so we're looking for this region bounded. And I mean, not the only way, but the best way, in my opinion, to figure out this region is to graph it. So what I'm going to do is graph all this and figure out what that region that's bounded or surrounded by these three things. Bounded just means it's like surrounded. So I have this graph right here. And we're going to x equals 2. So I'm probably going to deal with the x equals 2 first. Actually, let's deal with the y equals 0 first. Okay, so I'm going to color code this red. So I'm going to circle this in red. Okay, and y equals 0 is just going to be from here to here. Okay, now the x equals 2 is just going to be this right here. That's why I stopped with the red at 2, because it has to be bounded by that. I can't go past this. So this is, let me color code it again to be this. Okay, and the last one, this y squared. It's going to be a little rough, so bear with me. So I'm not the best at making curves all the time. All right, at 2, it's 4, so I just plotted a 4 there. At 0, right here, it's 0, so I'm just going to, oops, wrong color. Sorry about that. Come on, thing. Okay, let's do, where do we have green? Okay. We have 0 here, and then at 2, we have 4. Okay, now this is a parabola. I'm not going to draw it very well because I'm just not good at drawing these, but it doesn't matter. The main thing is we need to, yeah, because that's not exactly the best. That's okay, it doesn't matter. The main thing here is we need to figure out this region right here. That's the region that's bounded by these three things, which means it's in between all three of those things. If I picked this one right here, it wouldn't be bounded by this red, right? I guess it, well, no, it wouldn't be bounded because it would be unbounded. It would go infinitely many, because if you found this area over here, it's going to highlight the whole screen, which, why did I do that? Okay. You get the idea. It has to be in between here That's the bounded region. So right now we haven't really done any calculus. We just graphed this out. Are there any questions on the graph?
Nope.
I highly advise doing the graph first, just so you kind of get a visual of what you're looking for.
Yeah, do you know how to graph the x on the calculator?
Your calculator will not graph the x, but check this out. I'm going to show you a shortcut. Great question.
Ooh.
Here we go. So I'm going to graph x squared, and I'm going to graph y equals 0. Now watch, what you can do here is you can use window and then make your x max 2. So make this 2. Now that the screen is going to cut off at x equals 2. Does that make sense? Watch. Let me show you. Zoom 0 to zoom fit it. Oops. Okay. Now you can see that's the region we want right there.
Mm-hmm.
But we have all this mess right here. We don't want that. We know it's from 0 to 2. So I'm going to change this to 0. Oops. I should have done zoom 0 again. Watch this. Come on. Zoom.
Yeah, I see it. I did it. Pretty cool.
Yeah, my computer's like crashing here. Oh, there we go. Zoom 0. Okay, sorry about that. So now you can actually see the region. Okay, here's y equals 0, and then this cuts off at x equals 2, so you can get an idea. You can't get it to graph a vertical line, unfortunately. Okay, that's what's kind of nice about Desmos is you can graph all of these, including x equals 2. So then you can kind of see that region very well, because it'll actually graph the x equals 2. So it's this region right here. But your graphing calculator will not do it. So the best you can do is just change the window to stop there. So yeah, I haven't figured out a way of doing that. Maybe I can try to find something, but I doubt it. All right, back to here. Okay, so hopefully there's no questions on that. Now we are rotating this around about the x-axis. So I'm going to rotate this right here around here. So now it's going to form a really crazy shape. Hold on. You're going to have to bear with me on this one. It's going to end up looking something like, oops, I already did it poorly. Something like this. Okay. And we're rotating it around so it looks three-dimensional. So something like this. Oops. Something like that. Okay, so it's like a weird shaped cone, kind of. You can imagine that. That's the volume that we're looking for. Okay, it helps to draw it. I'm going to show you why in a little bit, but basically it helps you with finding the A and the B that we know from 0 to 2. It also, I don't know, helps you to understand that you're finding the area underneath x squared, not above it, but that's kind of obvious. And then in between y equals 0. There are some people that don't graph it. You can just imagine it in their head. That's totally fine. Okay, we're using the formula. It's pi times the integral from a to b. So we're going a to b. A to b, as you can see on this, it's from 0 to 2. And we're using f of x. I'm going to actually use the color code on this because it's green. And we're going to square that and then multiply it by dx. Okay, from here, I'm going to simplify this a little bit. F of x squared is just x squared squared, which is x to the 4th. I just don't feel like writing all this over again. So I'm just going to simplify it there. Oops. Okay, this means antiderivative, and then you plug in 2 and 0. So I'm going to do the antiderivative first. And plug in 0 and 2. Okay, you plug 2 in here, and you get 2 to the 5th, which is 32 over 5. You plug in 0, you get 0. So you're just minusing 0 here. So I plugged them both in and subtracted them. And your final answer is equal to 32 pi over 5. Okay, before I highlight this, I do want to check it. So we're going to check it on our calculator. But first, are there any questions on any of the work that I have right here?
Nope, seems pretty good.
All right, cool. Let's go here now. So we're going to do pi times math 9 from 0 to 2. So math 9 is your friend on this. Okay, now we're using that y sub 1, which is x squared. Well, I guess I could just, it's not going to take me that long. I was going to put a y1 in there, but you really don't need to do that. This ends up being x to the 4th. So it's 1, 2, 3, 4, and then dx. Hit enter on that, and you get that. Let's see if that's equal to 32 pi over 5. Pretty sure it is. It is, boom. So I'm going to screenshot this just because I'm going to include this in the notes. Okay, paste, put that over here. Definitely going to want to check these on your calculator each time. It does help to make sure you know you did it right. So take advantage of the fact that I'm allowing you to use calculators. Highlight this, and we're good to go. Questions on that?
You're good.
All right, cool. The next thing we're going to do is we're going to figure out the volume if we rotate around the y-axis. Okay, now just by looking at this now, try to imagine the shape of what this would look like if you rotated it around the y-axis. I'm going to put this over here. So we're doing the exact same problem, exact same bounds, only I'm rotating it about the y-axis. Can anyone picture that? Can anyone describe what that looks like? Put a line right here. Just
so the bounds are from 0 to 4, right?
Right. But what about the shape? What does the shape look like? So it looks like we're gonna come out of here.
Oh.
This is bad. Bad
like
drawing.
a cylinder?
It's definitely related to a cylinder, so it looks kind of like a cylinder. Oh, jeez, hold on. This is gonna be rough. This is so bad. Oh my gosh.
Bowl of soup.
It does look like a bowl of soup. Yeah, that's what I was thinking.
Yeah.
It looks like a bowl. It's just so hard to draw with this thing. Oh my gosh. Sorry. I'm using a graphics tablet, so sometimes it's one thing to write, but it's another thing to draw on it. Oh, jeez. That's terrible. I'm sorry. But can everyone see that it's like a bowl, kind of? That's so
Yeah,
bad.
we got you. Yeah.
Oh, it's a bowl, but it's filled in, so it's not empty. So there's still a volume to that bowl shape. Okay. I'm sorry for the drawing. I'm sure both of you can draw it way better than me. Are there still only 2 people here?
Yeah.
Yeah.
Yeah. Elena, sorry about the for whatever reason, that link stopped working. I don't know if it's through Abanzi's end or what, but the link stopped working, so I had to redo all the invite stuff, and then it didn't work again, so I had to redo it. So that's why there's all those emails. I'm like, oh, great.
Oh yeah, you're fine. I check it every day, so.
All right, cool.
Yeah.
Yeah, hopefully people check their email. That's the main thing they're supposed to do. All right, so we're going to do this exact same thing, only now it's with respect to y. So that means all the equations are going to change to y's. Okay, so this right here, it's with respect to x because it's y equals x squared. We need to basically solve for y this time. So now it's going to be y is equal to the square root. I'm sorry, x is equal to the square root of y. Okay, because our equation here, you see before we had this x in it. This has to be a y this time. This dx has to be a dy as well. So long story short, if you're rotating around this axis, I should have wrote it down. We're rotating around this axis this time. Everything's going to be in terms of y. Okay. Probably going to, well, I shouldn't say probably. The quiz that you're going to take on this is going to involve the x-axis, but the final, I believe, is a y. So it is to your benefit to get it right the first time because your final should be easier. Or, I'm sorry, the final is going to be harder. To me, x is easier because you don't have to switch this. It's one less step. But anyway, let's find the volume of this thing. So we are finding the volume of this one, and it's going to be pi. Now, this time we're not integrating from 0 to 2. As Lath said before, we're integrating from 0 to 4. So you have to switch that up. This is where the graph really helps because you can kind of see that you're integrating up this time instead of over. We're used to going over, up is a little bit different. Okay. Another thing you can do is, because y is equal to x squared and x equals 2, just square it and you get the 4. So you can change the 0 and the 2 based on the y equals x squared equation. Put in 0, you get 0. Put in 2, you get 4. So you can do that as well. All right, we are integrating with the square root of y this time. It's still squared, which actually makes this easier. dy. Now, is this volume going to be bigger or smaller than this cone thing? Any guesstimates?
Bigger.
Yeah, It is going to be bigger. I didn't draw this to scale though, because if you notice the 2 is way longer, but that's just because I drew it by hand and I just needed it for an idea. But I believe it is bigger. Okay, so that cancels. So you have an antiderivative of y, which is super easy. Should be super easy, I should say. And we're going from 0 to 4. So you do the antiderivative, you add 1 to the power, so you have squared, divide by that power, so you get that. You plug in 4, you get 16. 4 squared is 16. Divided by 2 is 8. 8 pi. You plug in 0, you get 0. So really your answer is just 8 pi. 8 pi. So it's a slightly bigger answer than the one we just did, because the other one's 32 over 4. This is 32 over 4. This one's 32 over 5. So it's slightly bigger. You wouldn't guess that by the drawing, though, because my drawing is so bad. But that's okay. All right, the only last step to do is to check this. Let's go to the calculator. So now we're going to have pi math 9 from 0 to 4 of the square root of y squared. So I'm just going to put y. You can just do alpha y like that. And then this has to be in terms of y as well. And then you hit enter. And then you get something like that. Let's see if that's equal to 8 pi. 8 pi. Boom. Now, say you didn't want to use x or y's. You can use x's on that. You can do the x and the x here. You're going to get the same answer because variables don't matter. It doesn't matter what letter you use. Oops. Paste this in over here. I get something like that. All right, any questions so far on these two parts?
Nope.
All right, we are going to take a break now, and I'm going to see if anyone emailed me and was like, hey, I'm trying to add to the lesson and I can't get in, just to figure this whole thing out. So let's take 5. Okay, this is where I basically made this whole section for you, so
Nice.
you should be happy for this next one. Okay.
Thank you.
Now, this quadrant 1's actually not needed because you're only stuck in quadrant 1, so it's kind of redundant, but it doesn't matter. So I want to figure out the area that's bounded by 1 over x, where x is greater than 1. Okay, so first thing we're going to do is draw this. Put a line here to separate this out. Okay. So we're going to draw this out here. Okay, so it's 1 over x, but it's greater than 1. So here's 1. Okay. And 1 over 1 is 1. So I'm just going to say it's right here. It doesn't really matter. Okay, now I'm going to graph this. I'm actually going to use a little tool here. Kind of helps a little bit. You can graph it however you want, though. But this one's pretty nice because it does the other end. Whoops, didn't want to do that. It does the other end for me. So you end up with something like that. So that's going forever.
Oh, and it's improper.
Mm-hmm.
Oh.
Exactly. And that's why it's kind of interesting. I'm going to change this color just because the main function is this red right here. All right. And then I'm going to rotate it. I guess I can do this again. There. Whoops. That's bad. So you have a shape that basically looks like that. Okay. And then you can see it looks like it's basically like a cone, a weird cone that goes on forever. Okay. We want to figure out the volume of this. Like you said, it's improper. So we need improper integrals on this. So the volume is going to be equal to pi. This is crazy, by the way. So we're going to go from 1 to infinity. Okay. And the function is 1 over x. We're going to have to square it. Dx. Okay. I'm going to simplify this just to make my life easier. Just going to write it like that right away so I don't have to rewrite everything. Since you're the only one here, just stop me if I'm going too fast or something.
Yeah.
So you have negative x to the negative 1, and we're integrating this from 1 to infinity, which you're not really supposed to write it that way, but that's okay. Okay, I'll write it over here. Okay, this is going to be equal to pi. Oops, jeez. Okay, we're plugging in infinity, so I'm actually going to use the limit here as b goes to infinity. So we're going to plug infinity in first. So you're going to have negative 1 over x minus, then when you plug 1 in here, it's just going to be negative 1. You with me?
Yep.
All right, so then why don't you, well, here, since you're the only one here, what is this limit approaching? If it's negative 1,
0.
0. This is 0. So what's your final answer then?
1. Oh, pi.
Pi. Now let's think about this for a second.
What?
You have a shape that's getting infinitely bigger, but the volume of it is finite.
Holy.
So why is that? Isn't that kind of weird? If it's going forever, shouldn't it? Think about it this way. That shape is going forever. So it's taking up more space. It has to. It's taking up more space. If it's taking up more space, then how is its volume finite? If it should just be taking up more and more space. Hold on, someone actually joined. Let's see who it is.
Elena, she's back.
Oh, you're back. Good.
Yeah.
All right, you haven't missed anything. We just started doing a practice problem right here. It's with 1 over x this time. And it's from where x is going from 1 to infinity.
Okay.
Okay. And then we worked it all out. We had to use limits. I will not be giving you a limit problem like this on your quiz. Okay. I don't know about the final because I don't remember what's on the final, but I'm pretty sure it's not on the final as well. But it's still good practice. And also, I think this is just really cool.
Yeah.
Okay. You have a shape that's getting infinitesimally bigger. Okay. But it's not taking up any more space after pi, which is crazy. But you can also think about it this way if you want. Pi, the digits keep going. So if this keeps going, then in a way it's just adding less. It's adding a smaller amount each time because it's just another decimal place each time. But it's doing it forever, like pi goes forever. So we're going to talk about this in more detail in a little bit.
Yeah.
All right, the next part. And Elena, you don't have to do this one. This is like strictly almost for lathe or just for anyone that wants to nerd out because this is really complicated now. This last part. It says compare the area of quadrant 1 with the volume from here. Okay, so now what if we just want to find this area right here?
Oh, that's
Okay.
interesting. Whoa.
Now this area is just going to be, the area is just a regular integral, so it's old school stuff from 1 still going to infinity of 1 over x dx. Okay, Lath, solve this. What do you get?
Oh, it's going to be ln.
Right, it's going to be ln.
Ln. Whoa, so it's infinity, right?
Yep.
What?
We're not even done yet. Wait till you see this. All right, so it is infinity because if you plugged in infinity, oops, hold on. That's supposed to be a b. B. If you plugged in b here, you would get ln of b minus ln of 1. And b is going to infinity. It's embarrassing. Hold on. Long story short, you are right that it is infinity. So if you limit as b goes to infinity of ln of b minus ln of 1, ln of 1 is 0.
Yep.
So now you have ln of b. Well, if you graphed ln b,
Just infinite.
that goes to infinity. Very good. So ln of x, if you put a bigger and bigger number and it just goes to infinity and never caps out. It goes to infinity very slowly,
Yeah.
but it goes to infinity nonetheless. So your answer is infinity for this one. Now, let's think about this for a second. Your area is infinity. So if this yellow part goes to infinity, but the 1 over x here, the volume, is finite. So if you want to think of it as area is almost like you're painting the outside of this.
Yeah.
Volume is if you filled up this cone. So if you had paint, this is called the painter's paradox, by the way, in case you want to look it up. You can fill this cone up with a finite amount of paint. It's pi paint, but you could paint outside of it forever. So try to imagine that in your head. You have some object where you can paint the outside of it forever, but you can't fill it with paint forever. It will never go over pi. That's why it's a paradox, because how can that be? Think about a shape in real life. How would that work? Does anybody know what the solution of the paradox is, or at least part of the solution?
I have no clue. What?
I mean, this is all mathematical. Mathematical is a language where you can imagine things. In real life, atoms do not get infinitesimally small. Eventually, there's a size of an atom. And if you go smaller than that size of an atom, for example, if you did this infinitely many, you wouldn't even be able to, well, yeah, if you tried to fill that up, eventually you're going to get, imagine this, you're trying to fill this up, but like you're rotating it like this. So you actually can fill it up. Whoa. Okay, so we're rotating it like this. And now you're filling it up. Eventually the atom is going to get stuck because these two graphs are going to infinitesimally closer. And as soon as it's closer than where the atom would be, it's not going to fill up any further than that. That's why it's a paradox, because we're thinking infinitely many, but you're not actually thinking in real life there's limits to everything. Okay? But you can make this infinity quite easily because of that.
See, I'm thinking every single time, like we can't comprehend infinity.
Right. No, yeah, we can't. I mean, I'm sure some people out there can, which is just really insane. And those are, those mathematicians and stuff like that. But yeah, we did not evolve to be thinking in this way, in my opinion. There's no like evolutionary benefit to think this way, but yeah, that's science. Now we're getting into science, but you can believe whatever you want. But yeah, the infinity thing that's the infinity thing. All right. So anyway, I'm not going to give you anything with infinity. I just thought that was cool that the area is infinite and the volume isn't. When this I think this happened in the BC's era before calculus was even invented. So I forgot how they actually did this, but it's called Gabriel's horn, because Gabriel's horn is like, it's got some Gabriel's horn, kind of like a whole history to it, but basically it's this thing right here, only goes forever, obviously. But it's based on the Archangel Gabriel, whose horn was to announce judgment. Okay, well, we're really getting into other stuff that's not math related.
Yeah.
But that's named after people's beliefs. And looks like a Christian belief. I don't know. I just think that's super interesting, and I don't know. Again, it's not going to be on a test or anything. And if I offended anyone, I'm sorry. I know everyone has different beliefs and stuff like that. I'm just telling you what it's named after. I'm sure other cultures named it something else. But when I was a kid, I didn't realize this, I think, until Coach K told me. Leif, if you know who Coach K is from the high school. And I thought Gabriel was like a mathematician that figured it out. This guy, Torricelli's the guy that did it. Oh, 17th century. I said BC. I was way off. Okay, either way, it was like around. And this was a huge argument. People were arguing so much for this. They were saying calculus wasn't working because of this. I don't know. It's crazy. Oh, there's a proof for it. Does it even have the painter's paradox? Maybe it's not called painter's paradox. Hold on. Paradox. Oh, yeah, painter's paradox. Here we go. This is what I was talking about. It would not be sufficient to coat the inner surface. That's what's weird. You can't paint the inside of the horn, but you can fill the horn up with a finite amount. It's just so like, it's our minds are not made for that. Some people's, most people's aren't. But, okay. Anyway, that's disk method. Yeah. Washer method is the exact same thing as disk method, only you subtract off a volume on the inside. And to subtract that off, that's what this minus g squared is. This f of x goes first because it's further. If you look at the radius right here, it's further than the g for any x here. So because that's further, it goes first. If you did it the opposite, then you would have a negative volume. If you accidentally switch these, just know that you can never have a negative volume. So just make your answer positive, and I'll act like you didn't switch them. I just don't want someone to accidentally switch them and then realize it at the end and go, oh man, and then they have to erase everything. Don't erase it. I'll just give you credit. Or do one of those arrow things that sometimes kids do. Some professors don't like that because I don't know why, because it's not professional, but none of this is really professional because we're learning it. But I will do not care. But if you do that, switch it. You should not have a negative volume because that's impossible. So, all right. Anyway, it's the same exact formula, only there's a minus g of x squared. That one's just f of x squared. Make sure it's in parentheses because you still have to multiply both of these by pi. So let's do an example. Again, there's not much curveball on this. Does help to graph it though, so let's definitely graph this. If you want to graph it on your calculator, by all means. I'm going to graph it by hand for some reason. I don't like that. Let's do this. Yeah. Oh, actually, hold on one second. Let's get rid of x equals 2. Okay, because a lot of times they don't actually give you another value. It says what's bounded by these two things right here. I don't know why that x equals 2 is there. I think it's I just forgot to delete it. But let's graph these two. Does anyone know the intersect on this? Actually, I mean, you can just graph it and check the intersection or just guess numbers. Does anybody know? Well, if you figure it out, just let me know. While you're doing that, I'm going to graph these. Actually, I'm going to figure out where the intersection is first. Okay, where they're equal, that's where they're going to intersect. I'm going to subtract off the x here. I'm going to factor in x. And then I'm going to solve. X equals 0, x equals 1. So that's where it's bounded by. So that's what I'm going to draw. I'm going to go to 0 and 1. If I put a 1 for both of these, if they're both equal to 1. So I'm going to put a 1 here. And now I'm going to graph. I'll graph the x squared first, just to get it out of the way. 0 here, the other one's 1. And then I'm going to graph a parabola the best I can. There we go. Then I'm going to graph the y equals x. Again, they have the same endpoints. I know this one's linear, so I'm just going to try to make that as align as much as possible. And you can see that's where it's bounded. Say you didn't want to do all this math, you can just use your calculator. I mean, you could have really just guessed and checked as well. X. Boom and boom. Now, this one went to 2, even though it intersects at 1. So I can change my window to the x max to be 1, and then do zoom 0, and it fits it to the screen. And you can kind of see that's what we're looking at here. Should have used the same colors on these, but it represents the same region that's bounded. Okay, so at least the yellow matches the color coding. Okay, now we are rotating around the y or the x-axis. I'm sorry. So we're going to put one of these in here, and the shape ends up looking. Oh, right, this is going to be a nightmare. Here we go. Okay, not very exact. That's okay. You have something like that. Let's use this light orange, and it forms some kind of a shape that looks like this.
There's a hole in between.
And then there's an empty space in there too, yes. And you can kind of imagine that empty. I mean, it's hard to imagine this though, maybe just for me. But you can imagine that inner cone kind of shape. And so you have a cone, and then there's like a weird cone taken out of the center of it. Essentially, that's what that looks like. So we're looking for that volume there. Oh, we should have done this around the y-axis too. I didn't write it down. But it forms like a weird, it's just a bowl on top of a bowl, I guess. No, it's a bowl that has a weird cone cut out of it. It doesn't matter. I'm just talking to myself here. Anyway, all right, so let's do this. The volume here is going to be equal to pi, and we're integrating it from 0 to 1 of, remember, the f of x goes first, whichever one is the furthest radius. So
Oh,
in that
why
case,
did we ignore x equals 2 again?
Oh, because that wasn't supposed to. If you did x equals here, if you did x equals 2, it's not bounded by it anymore.
Oh yeah.
Yeah, it looks like this. The 2 wasn't supposed to be there. It was never supposed to be there. Oops, I didn't even do this right. Hold on. Zoom 0. So you have it where it's bounded, and then you have like another weird shape.
Yeah.
So it's like bounded here, and then it's unbounded here because this goes forever. Well, no, it wouldn't because it would stop at x equals 2. Yeah, I guess we could have done it. I just don't want to.
Well, that's two
Personally.
different equations, right?
Yeah. And also, yeah, because they flip-flop. Right. That's a very good point. But also, it's not the problems when you get these, it's going to say what's bounded by. It's not going to have an extra thing like that. I'm not going to try to trick anyone with that because it's just not worth it. So it's going to be the orange first. So it's going to be x and squared, and then minus the red, which is going to be x squared squared dx. Now what I would do here is simplify everything first. So this is x squared minus x to the 4th. Otherwise, you're rewriting everything here. Like, why bother? Let's go straight to green here. All right. I'm going to do the antiderivative because that's what this means. Antiderivative, plug in 1, plug in 0, and subtract. So antiderivative here is 1/3 x to the 3rd minus 1/5 x to the 5th. And we're integrating this from 0 to 1. Okay, you plug in 1, you get 1/3 minus 1/5. You plug in 0, you get 0, which is pretty nice. And you end up with 5/15 minus 3/15, which is 2/15. So 2 pi over 15 for your answer. Is everyone still with me?
Yep, we're with you.
Yeah.
Okay. If you have questions, just stop me. I don't think it's rude. All right, so I'm going to quit out of here. All right, so now if I do pi times math 9 from 0 to 1 of x squared minus x squared, oops, that's not going to work, x, and then with respect to x, oops, it should all work out, hit enter. 0.419, basically, if we run to the 3 decimal places, that should be equal to 2 pi over 15. Boom. Cool. Screenshot this.
So that's the area of like around the hole, right?
That's the volume.
Yeah.
That's the volume of that shape. That looks like a loud horn or something. I don't know what it looks like really.
Yeah.
It's hard to imagine that.
I mean, props to you. Your drawing is pretty good. You're trying hard. Because if I was to draw that, I would
Yeah, but I've been.
Yeah, I've tried to draw that in my notes, and it's pretty awful.
Yeah.
I've been doing this for a while. The thing I like about drawing 3D is a lot of it like has rules. It's just you have to remember the rules. Like if this really rotated around, then it should be symmetrical. So then I tried to make it symmetrical as much as possible. Obviously, that's hard to do. Like this circle should like kind of dip like that. Like obviously, this is terrible. It should have dipped more. Like I don't know. I try to remember those like perspective.
As long as you get the point.
Yeah, that's the main thing. As long as you understand, that's all that matters. I'm not going to grade your picture. I do actually give more credit if you do draw a picture if you get everything else wrong. So if you got it right, awesome. But if you draw this and you still get something wrong here, I usually give a look. Because if you can draw it, then you understood the concept, in my opinion.
Wow.
You drew it and you showed the right. You understood what to do. You just might have messed up something little with the calculus. So when in doubt, draw it out for sure. All right, are there any questions on that before we get to the last part, which is probably the hardest section?
No, you're good.
Nope.
Cross sections?
Yeah, cross sections are a little bit brutal.
Let's get this.
All right, for cross sections, this is how I draw them. I advise drawing it this way. Actually, Laith, didn't I talk to you in class about the best way to draw this? I think we went over this. I had so much trouble. Maybe it wasn't your class. I don't remember. But you can't draw them like we were drawing these before, where you have, like, imagine I drew this thing right here, this, and I'll do it in blue. Imagine if I drew this again, it would look something like this. You can't imagine squares coming out of this, because if you're looking at it dead on, it's just going to be a line. Do you know what I mean? Like, how do you draw a square coming off of this? It's like really hard to do. Like, it doesn't even, so that's why I tilt it, because I couldn't think of another way of doing it. So that's why this is the Y, this is the X, that's F, and the squares are coming off of it. It just that illusion of depth, it helps with that. And I try to draw 2, 3, or 4 shapes of whatever shape it is for this. These are so complicated, let's just get started. The main thing is you're integrating from A to B of all the areas of each of these shapes. So the area of this is base squared. So it's whatever the base is squared, because that's base times height. For a square, it's just the base is the same as the height. It doesn't matter. We'll go over an example, and hopefully this makes more sense. There is there's probably a thing here. A good rule is you can't practice these too much. I mean, I guess unless you're losing sleep practicing them so much, but like, it's good to practice these a lot, is what I'm saying. I would practice these until you can't get them wrong. Is a good way of thinking about it. Sometimes people practice until they get it right, and then they stop. They're like, oh, I get it, and then they're done, but no. Okay, I'm going to use a ruler here to graph this out, but just kind of do a tilted XY axis. So you end up with something that looks like this. Okay, I'm going to label this just for fun. You don't really need to do this, but this is Y and this is X. Okay, the base of the solid is the region. So we're going to draw the base first. It's the region that's enclosed by this parabola and the line x equals 1. So I'm going to actually graph x equals 1 first. I'm going to use my ruler to do it. Let's do this. Let's do this. All right, I'm going to graph x equals 1 in red. I'm going to color code it. So this is my red. Okay, I'm going to do the other one in orange. Now we're only going to 1, so I'm going to plug 1 in here, and you should get 4. So I'm going to graph 4. Whoops, that's white. Let's do black. Okay, so I'm graphing 4x squared. Goes from here to here. This is really hard to draw because I don't even know. You're trying to make this look like a parabola. That does not look like, oh, maybe a little bit. But those are never fun to draw. But the base is what's enclosed or bounded by whatever I just drew right there. So this part right here, that's the base that I'm going to draw all my, in this case, squares. Okay. If you notice, the base here was this blue weird shape. This time the base is this yellow shape right here. And we're going to draw squares based on that base of the shape. Okay, so squares are going to be coming off of this thing. Okay, I like to start with the smallest possible square that I can draw. I'm going to really zoom in here. Okay. So the square coming off of this is going to have the base from here to here. And oh, I should say, it says that it's perpendicular to the x-axis right here. It says the solid is perpendicular to the x-axis as a square. So I'm drawing squares that tee up with the x-axis. Otherwise, they would tee up on the y-axis like this. But if you notice, the base of the square is teeing up on the x-axis. Your quiz will also be x-axis, just so it's similar. You can, here, let me just finish this square first. So you have this square coming off of it like that. Okay, if you drew one off the y, perpendicular to the y, it would look something like, oops, it would look something like this, like that. If you can kind of imagine that. Don't draw these because, again, this isn't part of the problem, but you can imagine squares going that way. We're going the other way, or these squares. I just wanted to show you what it looks like. Okay. That's one square. I usually do like, I don't know, 2 or 3. Try not to make them overlap just because it gets really sloppy if I do that. Okay. Squares coming up. It's got to kind of like look like the same length here, but you have to also take into account the depth. Sometimes if you zoom out, it looks better. Okay, and then I'm going to draw the last square. Holy cow, this is going to be humongous. I shouldn't have done this one. That's terrible.
Do you
That
end
would-
up like subtracting off the extra space?
What do you mean extra space?
Like the white space and the
Like this space right here?
yes.
No, you have to imagine that this whole thing is a sheet that goes all the way up and then it's filled.
Oh,
Like
okay.
here, actually, I don't know. Were you here for the beginning part when I was showing that one graphic? This?
Okay. No, I wasn't.
Oh, okay. Then here, let me show you. That's why this. Okay, this is way better than anything I could ever draw. So we're doing squares. The base I can't change because this guy made it where you can't change it. He programmed all this. But what you can do is imagine a square along this whole thing.
Oh,
There's
okay.
infinitely many of them.
Okay.
Yeah, it's almost impossible to like.
To draw, yeah.
Yeah, because they're transparent and like, but they're supposed to be colored in. But the thing is, if you notice, like this is what you would be looking at if it was a normal XY. You see how they're just flat? So that's why we like I tilt the graph like that so you can actually see all the squares. But even like 10 is too much. Like, I don't know. I mean, you can get it because it's transparent. You can see through it, but like I can't draw that. Like this is so bad. Like this one's not bad. Like these have to be parallel. Like
That makes more sense now.
yeah. No, these are not easy. So any questions would be more than welcome here. But anyway, so you're adding up. Imagine there's infinitely many of these stacked up just like this. It forms like a shape. Like this is not infinitely many. This is 100, but you can kind of see it looks like infinitely many. There is a volume to this shape. And they're all squares. That's what's weird about it is they're all based on squares. If it was a triangle, it would look like this. See how it's like a triangle? I don't know, then circles would be like a dome or semicircles, I'm sorry. I don't know. It's crazy. I'm so glad that people program this. I couldn't imagine teaching this without computers. It'd be a nightmare. But that's why I'm drawing them. It actually doesn't help to, I don't even know why I'm drawing them really. So you can draw them poorly. It's not going to change anything because it's just getting an idea of what it looks like. Now, the formula for this is integrating it from A to B. A to B in this case would be 0 to 1. If you ever don't know the limits of integration on a quiz, ask. Just be like, is it 0 to 1? I just want to make sure, and then I'll tell you. So I don't want anyone messing up the A and the B. Now we need an area formula for each individual square. So what we're going to do is we're going to find what is the area of just one of these squares, and then we're going to integrate it throughout all of them. The area is not going to be a finite number. It's going to have like an X in it because all of these are different. They're all going to have different X's. So we need to figure out what this base is right here. I'm going to say it's B1. But what is this base right here? Well, it's defined based on the distance from the x-axis here to whatever this orange function is. Well, the orange function is 4x squared. So since that's 4x squared, that base distance is equal to 4x squared for all of them. So if you wanted to look at the distance between here and here, it's still 4x squared. The x is different. Like maybe this x is like 0.25 and this x is 0.5. So the distances are different, but it's still based off of 4x squared. This part right here, this pink line right here, that goes from here to here is still 4x squared. So that makes it kind of nice. So the area, let's do that in magenta. The area of one of these, just one of them, is equal to whatever the base is squared. And we just said the base is equal to 4x squared. So this means your final area formula is equal to b squared, which is 16x to the 4th. So I would always find the area of one of them first, because once you find the one, you can just integrate it and it finds all of them. Are there any questions on finding the area of just that one?
Nope.
All right. Let's go with green. Okay. So we're going to do the volume. Oops. We're going to do the volume is equal to, there's no pi. I was going to write pi. That's embarrassing. We're not doing anything rotationally. There's a little tip for you. Anytime you see a circle or sphere or anything like that, you're going to see a pi. Okay, that's why pi is so important, because a lot of the physical models that we use in chemistry and physics, it assumes that things are spherical objects. Atoms are spherical, electrons, protons, spherical. Okay, when you find the center of mass of an object, you're acting like that whole object is a sphere and the center of mass is whatever the center of mass is. So there is no pi in this, long story short. Try not to mess that up like I almost did. We're integrating it from 0 to 1. And you're putting the area formula in here, which is that 16x to the 4th. And there's dx because that's part of the formula. You're finding an area, and the area is based on the function. So it's a of f of x. Okay. The f of x is 4x squared. So it's like b is the 4x squared, and you squared it to find the area. So we have something like this. The rest of it is a very, very basic antiderivative. Okay, you just use power rule. I'm going to pull the 16 out, and you have 1/5 x to the 5th, and you're integrating it from 0 to 1. Now, 0 is awesome because when you plug that in, you just get 0. So you just have to plug the 1 in. So you're going to get 16 over 5 minus 0. 16 over 5 is the answer. We should check that, though, just in case. Did anyone get 16 over 5?
Yep, I got it too.
Well, I mean, this one's kind of easier, but let's test it in the calculator anyway. So we have math 9, 0 to 1 of x to the 16x to the 4th, 16, 1, 2, 3, 4, x to the 4th, x, enter, math, frac that up, 16 over 5. Awesome. Let's do hold on 1 second. Hold on 1 second, everybody. Do you have to move my car? Is there a spot for my car somewhere? Yeah. Okay. Sorry, I would do it, but I have class. All right. Sorry about that.
You're good.
Someone's like moving in or something, and I'm parked in my driveway, but it's blocking that.
I thought you ordered food.
Oh, no. I actually got some sushi earlier.
Oh,
I haven't had sushi in so long.
it's good.
Anyway, oh yeah. This is that's the answer that shows it right there. And again, if you notice, I could have drawn these squares terribly. You still get the same answer regardless. It just, I don't know. For some reason, it helps me make sure I got the right area formula. But not an easy problem, to say the least. All right, questions on this? Any clarification needed?
All good.
I'm good.
All right. Here's one that's a little bit more complicated. It's a good one to do. The practice final is also a really good one to do as well. But first step is to draw that fancy X. Well, I mean, you don't have to do this, but again, I would draw those fancy X, Y coordinate plane.
Is that 2x minus x squared?
Yeah, 2x minus x squared, yep. I can bring that down. I mean, you can kind of imagine what that looks like. It's just a parabola that's negative. This is a good one to do. Better save. Okay. Okay, so first thing we need to do is figure out what this graph even looks like. And you can do that by graphing it or just kind of knowing parabolas. I would graph it just to be safe, though, because sometimes people think they know what something looks like and they don't. Zoom standard. All right, so we have something like this. That's the shape that we need. Let's do this. And I'll try to match the colors this time. This is the base of the solid. Whoops, I didn't want to do that. Hold on. This is the base of the solid, that yellow right there. And it says the region bounded by the graph and the x-axis. So this is bounded with the x-axis right here. If you try to like do this part right here, it goes forever. Again, you'd be highlighting everything. It's not bounded, it's unbounded. It keeps going forever. This is trying to fill up everything. Let's get rid of that. Okay, so I'm gonna graph this here based on this thing right here. I don't think I can actually move this. Oh, actually, hold on. This might do it. 2-point mode. I'm wasting time right now. This might actually do it. I don't know what that does. Never mind. That's embarrassing. All right, let's just draw it. All right, clearly it intersects at 0 and 2. Also, you can just test it up here really quick in the formula. If you plug 0 in, you get 2 times 0 minus, here, let's rewrite it. If you plug in 0, you get 0. If you plug in 2, you get 0. So that is what we want. This is going to be 2. And it doesn't really matter how you draw this parabola, so I'm just going to draw it like that. Okay, and then I'm going to highlight it yellow just so it matches the calculator graph, and now you can kind of see what that looks like there. Okay, now this one, it's equilateral triangles, so I have to draw triangles here, and the triangles are the base, based on this base right here, and they're perpendicular to the x-axis. So the base of them they're gonna end up looking like this. They're not gonna end up looking like this. There is a difference, believe it or not. All right, so I'm gonna end up with a equilateral triangle that looks something like that. I'm gonna end up with an equilateral triangle that looks like this. Here. And then I'm just going to make a smaller one because they're easier to make. Okay, so you end up with something like that.
Well, we know the base, which is the function. How do we find the height?
Okay, I'm actually going to make your life a lot easier on this. If you wanted to, don't write this down, but if you wanted to, you can easily, this is the height, it's 90 degrees. Here's the base, this whole thing right here. Okay, now technically this is the base as well. You can use Pythagorean theorem to figure out this height right here. Oops, why did I put X? I should just put H, it doesn't really matter. Well, let's put an H there. You can easily do all that, okay? It wouldn't even take that long, but I'm just gonna give you the formula because I don't care about the geometry. This is a calculus class. So whenever you get an equilateral triangle, I will give you the area formula for it so you do not have to memorize it, but in case you do care, well, no, we need it for now, so I'm gonna have to tell you now. The area of an equilateral triangle is √3/4 times the base squared, okay? And I looked this up already too, just to make sure. But if you ever do need a formula, you can always just do that. Area of equilateral triangle, and it's right there. Only we used B instead of A. Okay. I did that in my other lesson because I just wanted to make sure I didn't mess that up. So, but we need B in terms of X. Okay. The area has to be in terms of X. So, we do know that that B is equal to what? Any of the B's. Yeah, 2x minus x squared. Any of the bases are going to be equal to 2x minus x squared. Now the base squared, you just square both of them. So you just throw that in there. And then you get your final area formula in terms of x is going to be equal to √3/4. Now I'm going to square this all out because it's an easier antiderivative if we do that. So it's going to end up being 4x squared minus 4x to the third plus x to the fourth. You get something like that. Okay, I basically just expanded this out here. So now the next thing we need to do is say the volume is equal to the integral from 0 to 2. You can see that from the graph. And you're going to have root 3 over 4. And we're going 4x squared minus 4x to the third plus x to the fourth. Dx. Okay, remember this means antiderivative, plug in 2, plug in 0, subtract. So we're going to have root 3 over 4. I'm going to do the antiderivative real quick here. 4 thirds x to the third minus x to the fourth plus 1/5 x to the fifth. And we're integrating that from 0 to 2. Awesome thing about 0, again, all that's going to be 0, so it works out. So now we just have to worry about plugging in 2. So you plug in 2, you end up with 8 times 4 is 32 over 3 minus 16 plus 32 over 5 minus 0. I'm not going to put that in. I'm going to check my work because I just don't want to be wrong on this. Did anyone else get this?
Yeah, I'm doing it with you. It's very good.
Hold on. I feel like I did something wrong. Oh, no, I didn't. Okay. Sorry. All right. Divide everything by 4. Okay. Now 8 thirds. Let's just do 15 as the common denominator. So we're dividing by 15. This one's going to be 40 minus 60 is negative 20. And then multiply this by 3 is 24. So it's going to be 4. 24 and negative 20. And then times the root 3, you should get 4 root 3 over 15. You obviously don't have to do that in your head at all. You can just throw that all in your calculator. Not the root 3, but this whole part right here. Your calculator will do the fraction for you. Use the tools you have. I'm going to go back to the calculator here and work this out. So you end up with math 9 from 0 to, was it 1?
2.
2. That's embarrassing. Okay. And it's going to be 2x minus x squared with respect to x. Hold on. That's embarrassing. Times root 3. I'm just going to restart this. I forgot the root 3 over 4. Come on, Leith. I blame you. Just kidding. It's my fault. All right, ready? Insert. All right. Square root of 3. Oops. Insert divided by 4. There, now it should work. Ugh. Okay, 0.462 basically. So let's try that out here. So it's 4 times the square root of 3 divided by 15. Yep, it works. Cool. So we know that that's the answer.
Nice.
And you can say with huge certainty that your answer is right. If it happens to match, very unlikely that you did something wrong, unless you set up the original problem wrong, but trust in your calculator is what I would say. All right, questions?
I feel like
All right.
we're doing
Oh,
a
go
lot
ahead.
of it. We're doing a lot of integrals like these past couple of weeks, and I'm like, I can do most of them in my head. Not most, but few of them.
Yeah, if you can do it in your head, then do it in your head.
Yeah.
By all means. I need to write it
No,
down because the more I try to
Yeah.
do something in my head, the more mistakes I make, and I don't really want to do that.
Yeah, no, but I'm starting to. You know, it's a weird thing
Good.
because I've been doing it for a while now.
Yeah, what I would do if I were you, if I was anybody, is I would try to do them in your head as much as possible. So just look at it and try to work the entire thing out in your head and then get an answer and then actually work it out and see if you were right. Because if you practice that enough, if you practice doing all of these in your head over and over and over again, every time, even if you're wrong, you're going to figure out what you did wrong. And then you can actually eventually practice to do, you can always do them in your head then, or at least get close to it. So like right away when you look at it, okay, what does that look like? What's the region bound by that? Oh, what do I know? I know about negative quadratics. It's a negative quadratic, so it should point down. Like you could like start thinking about, so then it looks like that, and I'm making triangles, so then I know the area for that. But you're just, again, imagining all the steps in your head. You're not imagining it all at once. It's just good practice. It's good for your brain. I would never say do it all in your head because that's, you're gonna make a mistake.
No. Yeah.
Plus, like, you're gonna be an engineer. Like, your whole job is finding work, like showing people how you did your job, because you're designing things that have never been made before. You're not, like I think I told you before, like, there's no answer keys when you're an engineer. Like, you have to, prove to your boss or prove to other workers, this is the best way to do it because of this. It's not going to be like, oh, well, hold on, let me see if you did it right by looking the answer up in the back of the book. It doesn't work for any job. You know what I mean? There's no, unless you're a teacher, that's basically it. But
Looking forward to it.
Oh, because you're going to be a teacher.
I'm going to be an engineer.
Engineer, right? Yeah.
Nice.
Yeah, that's why I got out of engineering. I am not good at, I'm good at like designing software stuff because I was a coder, but like to design a bridge, I was like, oh man, there's just so many variables. I'm not interested in this. And then, like I feel like a lot of engineering is like guess and check. Like, okay, I'm going to try this model out and then make a computer simulation for it and see if it works. Okay, back to the drawing board. That bridge fell apart. Let's do another one. And that's before you even build it. Like, you have to do all the simulation and models and all that other stuff before you even, I'm like, this is too much. I'm good at like,
I don't know. It's so satisfying though once you're done.
Yeah, because you have an engineer's brain. I don't. That's the thing. I'm more of like a scientist. Like, when I was a chemist, as a chemist for like 18 months, all I did was work on cancer drugs, and I studied cancer drugs. I experimented with different cancer drugs. I didn't design anything. You know what I mean? I was, if anything, the chemist I was working for was designing the drugs, and like we were like helping synthesize them, and like, but I wasn't, I wasn't inventing anything. Like, I was running trials, which is important. Like, everything is important. Everything's got a certain, everyone's a cog in the machine, but like engineers are just, that's why they get paid so much, is because you have to have a special brain. You have to design things in your head. And I don't know, it's insane to me. So I give it props to it. I was an engineering major for less than a year in college, and I was like, oop, not for me. See ya.
Well, it's going to be rough for me when I start fall courses, because I have an engineering class, and it's like right around from and it's right around from 6 to 9 p.m. something like that.
Oh geez.
Yeah, and it's all hands-on stuff. It's like we're going.
We talked about this before, but Wabanzi's so much cheaper than going anywhere else. Like, well, I don't know why. How anyone
I went to an engineering school my freshman year, and it was like now I'm 20 grand in debt, and for what?
Right. Oh yeah. Yeah, no. When I was a kid, there was no college. I mean, there was college loans, but you didn't spend the rest of your life paying them off. Like, this whole generation, that's why when people are like, this generation's so spoiled. It's like, how are you spoiled? You have it worse in every possible way. Like, I'm like, I don't know. You get paid, like, minimum wage is the same as like now than it was when I was a kid. Like, and everything else has gone up in price. So like, everything is more expensive for you. College is more expensive. People are living at home longer. Your parents are going broke, so your parents are going to have to
raised minimum wage like $2 since I was like started working, and that really makes me mad.
Oh yeah. See, like, that's just, I don't know. It's the whole, I don't know. Anyone that says that you guys have it easy is just very confused. It's like talk to them and see how easy they have it. Oh, they're just lazy. Every generation says that.
Yeah.
Like, didn't I show you that one quote from Socrates or something? Socrates, lazy students or lazy kids or something like that. Maybe it was Plato. I don't know. Yeah, look at this. This is Socrates in the 500 BC. Children now, here, look at this. Children now love luxury. They have bad manners, contempt for authority, show disrespect for elders. Like, this is like this quote, and this is real. Like, this is a real quote. So it's like, they contradict their parents, chatter before company, gobble up dainties at the table, cross their legs, tyrannize their teachers. All right, Socrates, relax. But all right, should we take a break before we do those practice finals? 5 problems?
I'm
That's the
done.
next thing we got.
Sure.
Take 5?
Yeah.
Sure. Why not?
Okay, and then remember around an hour and like 50 minutes, my microphone goes bad. So if that happens, just tell me and I'll fix it. Set
Okay.
timer for 5 minutes, please.
Okay, 5 minutes and counting.
All right.
Mr. Ozarka,
Yo.
I'm gonna send you a YouTube link, and I want to know if you've seen this video yet.
Okay.
It's I just saw it the other day, and I'm gonna put it in chat. But it was very intriguing to see. I don't know. It's how will the future look like? Journey to end of time.
Okay, 37 million views. Holy cow.
Yeah, watch it at a later time for like 29 minutes. All of it, yeah. But it's like crazy. It's like it tries to predict everything. Yeah. But it's like all based on theories and stuff.
The thing is, he's a musician. He's an art person. So sometimes art people don't take into account reality, because art is so much cooler. You can make things way more awesome. But if this is like evidence based, then I'm all about it.
Yeah, no, it's like scientist, evidence based. Yeah. But then it
Holy
says,
cow.
yeah,
I'm definitely gonna have to watch this.
Yeah, watch it later on. But like, just like it speeds the timeline every year by like 5 seconds.
That's awesome.
And then like when I watched it, I was like, what? Yeah, it takes you into trillions and trillions and trillions and trillions of years of how will the universe start. But yeah, or end. Sorry. Yeah. That's weird to think about.
I will definitely take a look at it. Thanks for sharing.
Yeah, no problem. Yeah, because it's like the the stuff that they did, like the amount of production that went into this is crazy. It like looks like a documentary or a movie.
It also looks like it's really high res.
Yeah, it's 4K.
Like the images look really good. I double speed it though, so it's going faster.
Yeah.
Oh wow, it goes to the end.
Yeah, to the end.
It goes until the sun explodes.
Yeah. See, look at that timeline. Million, trillion, trillion, trillion.
Holy cow.
Yeah.
Okay, wow, I really passed it.
Yeah. Yeah, but it will also go into the theory of like multiverses as well. Yeah. And how will the stars all die out?
Crazy.
Black holes.
Yeah, this seems like it's informed. Yeah, this guy's professional. Man, 37 million views. We better get paid for this. You know how expensive this is to design, to animate? You can even imagine.
But I think that's in 3ds Studio Max. Have you heard of that one?
What is it?
3ds Studio Max. It's like a architectural graphic design program thing for like 3D shapes and stuff like that. It's pretty cool. Yeah, but I worked on all of the Autodesk stuff, Inventor, Revit. Yeah.
Yeah, I use Sketchbook.
Oh yeah.
Have you noticed that?
Yeah.
And this is all sketchbook because it's like you're on a piece of paper. Like you can do however you want it, write however you want. And then I have a graphics tablet, but my graphics tablet's not connected to the screen. So I'm writing with something on that, like, it looks like I'm just writing on a blank piece of paper, but the writing comes up here.
Yeah.
So you have to like shift your brain into thinking. Do you know what I'm talking about or no?
Mm,
Do you know
Yeah,
what a graphics
I
tablet
do.
is? Here, let me show you. This is a graphics tablet. So this is what I'm writing
yeah.
on, and it goes on the screen. Why are we recording this? You really don't need to record. But so when I'm writing it, I have to look at the screen to like see what I'm doing. But all right, are we ready to go for the practice problems? The timer just went off.
Yes, sir.
Yeah.
All right, cool. Save that. All right, is it this one? I think so. Yep. All right, here we go. And this matches what's on the website too. I just screenshotted them so it's faster this time around. But it says find the volume of the solid generated by revolving the region bounded by the line and the curve about the x-axis. So you have two functions. So what method do you think we're going to use? The washer method or the disk method?
Ooh.
If there's two of them.
Washer.
Right. And if I went over this in the last class, but not this one, a washer, the reason it's called washer is because of these are called washers. Okay. And you can see it's like a disk, only there's part of it missing. And so it's like washer method, only there's a part that's missing in the inside of it. So that's why it's called.
The first
good
time
for,
I
like,
heard of it, I was like, washing machine.
Yeah, me too. It should be called donut method. Called donut method.
Yeah.
It's more fun.
Mhm.
But I'm
Yeah,
just
I
a
got
teacher.
that, but
All right, so we're doing this here. Actually, let's go both ways. All right, and now to figure out where they intersect, you can do one of two things. You can set them equal to each other, or you can graph them, whichever one's easier for you. I'm going to just set them equal to each other, I guess, because I don't think they're going to be too bad. It just ends up, you end up having to do some factoring. So you end up with something like that, minus 2 minus x. And this is going to factor to x minus 2 and x plus 1, which ends up being 2 and negative 1. Now, if you graph this on your graphing calculator, it would be negative 2 and 1 as well. So what I'm going to do is graph negative 1 and 2. Okay. Now, from here, I'm going to, we'll do this one in yellow, or red, I'm sorry, and we'll do this one in orange. Okay, they intersect at those two spots, and if you plug in negative 1 to this one, it ends up being 2. If you plug negative 1 into this one, it also ends up being 2. So what I'm going to do is just graph out, let's just say this is 2 right here. Whoops, that's kind of sloppy. This is 2 right here. So that's there. And then if you plug in 2, you get 5. Let's just say this is 5. Okay, and then we have a parabola. Jeez. Almost. I almost had that one. Okay, the other one's linear. You know it intersects here and here, so I'm just going to do that and then just straight line it through. And we're rotating this about the x-axis. So you can kind of imagine what that shape is going to look like. It's kind of hard to imagine that one, actually. It's not the easiest one to look at. Okay. Something like that. That's not the greatest. That's okay. And then we'll do this right here. Something like that. rotate it around. Okay, so with that empty shape in the middle, as you can see, and then it's gonna be a donut with a really weird shape. If you can imagine that, it's kind of weird. A lot of these are weird. It's okay. So your volume is equal to pi. We're integrating it from -1 to 2. And the one that's the furthest radius away is the orange. And you're subtracting off, whoops. And then you're subtracting off the red. It's something like that. Okay. Now, this one, if you expanded it out, it would just take a really long time. So well, whatever, we'll just do it. Just ends up taking a bit. -1 to 2, and you end up with x squared plus 6x plus 9, all subtracting x to the 4th minus 2x squared minus 1 dx. Did anyone else get that?
Yes. Wait,
let's.
no.
Uh-oh.
No, never mind. You're good.
All right, so this and this are going to cancel, so you're left with -x squared. There's an x to the 4th. I'm going to put that in front here. 6x, there's no other x's, so I'm going to do plus 6x. And then 9 minus 1 is 8. I haven't done any real calculus yet. It's just all algebra. Jeez. Okay, I'm going to do the antiderivative here. 1/5 x to the 5th minus 1/3 x to the 3rd plus 3x squared plus 8x. And we're integrating this from -1 to 2. Holy cow. All right. So you end up with 32 over 5 minus 8/3 plus 12 plus 16 minus, then you plug -1 into all of these. Holy cow, it's a mess. I hope we did this right. Doing an awful lot of writing here. All right. I would just use your calculator at this point to add all these up. One 183 over 5. I wonder if that's right. I'm going to check this really quick. 1 to 2.
I got 117 pi over 5.
Over 5, yeah, that's right.
Oh, okay.
And you got the same, you wrote the same thing that I did that I have on the paper right now?
I wasn't looking at your paper. I was just flowing my own. Yeah, you look good. Yep.
8 over 3 plus 12 plus 16 plus 1/5 minus 1/3 minus 3 plus 8. Yeah, no, I did something wrong. So I'm not getting the same answer.
What did you do? The expanding was correct.
This is a nightmare. Oh, I see it.
Negative
negative.
x4? Yeah.
Right. Yep. Always assume you're wrong. Easy fix. Make all these negative. All right. Good. I was just testing you. There we go. 117. Or wait, was it?
117 over 5.
Yeah, 117 over 5. Uh-oh, I got 119. I did something wrong again.
Ooh.
Oh, whoops. This is also positive. That's embarrassing. There we go. Here we go.
The negative distribution.
I did it for that negative. I just forgot to do it the other negative. But that works. And that is the answer because I just checked it with my calculator.
My algebra sometimes is iffy. Sometimes.
I'd rather go fast and check than take a really long time and not go through it twice.
Yeah.
I don't know. That's just the way I am. All right. So we got pi math 9 from 1, negative 1 to 2. Yep. X plus 3 squared minus x plus 1 squared dx. And okay, and then we ended up with 117 pi over 5. Cross your fingers. Boom. Save. Cool. All right. This next one, you have to use your calculator to solve it. There's no way around that.
Arctan?
Yep. But that doesn't really matter. You're just making your calculator do the antiderivative of arctan. So you don't need to worry about it. But set it up, graph it. You're not me. All right, let's do this. This is a really good one to do because it shows how to use your calculator. It shows a good example of using the calculator for these problems. All right. First thing I'm going to do is actually see what this looks like just on a regular XY coordinate plane rather than this tilted one, just so I can graph it a little bit. So it says arctan, horizontal line, and vertical line of 1. So I'm going to do that really quick. So we have arctan, y equals negative 1, and then the x max is 1. So I'm just going to cut it off by going to the window and hitting that. And then graphing this. So you end up with something like that. All right, so you can kind of see the bounded region. It's this thing right here. 1, 2, 3, 4. I'm going to go to negative 4. I'm going to zoom in a little bit here. Oops. Negative 4, and then I'm going to do zoom 0. I'm going to fit it to the screen. So you can kind of see this region over here is what we're looking at. I mean, you can kind of imagine how hard that would be to draw if you don't really know what arctan looks like. So So this is definitely a calculator problem. It would be hard to do this without a calculator. So let's blow this up. I'm going to try to do the color coding matching this on as well. So we're looking for this. Whoops. I didn't want to graph all that or shade all that. Let's just do this. We're looking for this whole part right here. Okay, so I'm going to transfer that graph onto this thing right here. We are going to x equals 1. So let's just say this is x equal to 1 here. And whatever this intersection here is, looks like a weird intersection, so you're going to have to do second calc 5 to find that intersection. 1, 2, 3.
Like
Holy cow.
1.55, yeah.
All right, I'm going to
Store it.
Oh, yeah, I'm definitely going to store it, but this is definitely going to be.
Oh,
needed
buzzing.
here.
Buzzing alert.
All right, I got you. Check 1, 2, check 1, 2. Can you hear me?
10-4, you're good.
I'm actually going to use this graph over this one just because it's got the intersection already in there. Okay. So we're looking for, this is the base of the solid. And we're going to be putting, what are we putting on here? Which shape? Square. So we're going to be putting squares off of this. Okay. Holy cow. Okay. I'm going to say, let's see here. I'll do orange for this. I'm going to say that A is equal to this value right here. So that way when I put it over here, I can just put A. Okay. And then I'm going to do my best to graph this. Again, it doesn't actually matter if it's perfect or not. So don't worry about that too much. All right, so -1. Oh, I should graph -1 as well. Again, this is the Y and this is the X. Okay, let's see here. So right here, this was red in the graph, so the calculator, so let's just make it red here. Okay, and then the other one's blue. So from this blue, going from here to, doesn't matter, it's up here. It doesn't really need it. You don't really need to know that value. It does go through 0. This is going to be crazy to draw.
That's actually pretty good.
Yeah, it's a little wobbly here, but thanks. Thank you, sir. Okay, and then we're going to go all of this right here. Oh, I should have graphed x equals 1. Oh, that was off. That is embarrassing. Yeah, this blue needs to keep coming. See, that's so off. Oops. Okay, drawing this over here. There we go. This does not need to be here. Okay, you get the idea. All right, now we have to draw some squares. Again, you don't have to draw these if you don't want. It just helps me. Okay, here's my square. Looks more like a rectangle. I'm not going to draw a third one because it's going to be humongous. So you get the idea with 2. All right, so the area of this is going to be equal to base squared. This is the base right here. By the way, you're not really supposed to put B on both of these. That's why I put B sub 1 and B sub 2. If you put B, it looks like they're equal. That being said, I accidentally did do that on some of the answer keys. So if you see that, I apologize. It doesn't really matter. Just know all the B's are not the same. That's why you have to use subscripts. Okay, let's keep going on this. So the area, the base is equal to arctan x. Oops, I lied. Plus,
Yeah, the negative.
sorry, I should say minus this whole part right here. So you can just do a +1 if you want, or minus -1. It doesn't matter. But this whole base goes from here to here. So you need part of this arctan to this here. Now here, you can do it's this arctan, which is negative. So when you add 1 to it, it's still going to work here. If you imagine this, here, let's do this. If you imagine this distance right here, this is the arctan. Here, let's do this. This is the arctan from here to here. Okay, because arctan is defined based on the x-axis. It only goes to then. And then eventually you have to add this other 1. So you still have to add all this. This right here is just another 1. How do we know it's 1? It's because it goes from 0 to -1. So that ends up being arctan of x +1. That is kind of tricky because the other ones we had didn't do that. So that means, and you can see why you need a calculator on this, the area is equal to the arctan of x +1 quantity squared. Holy cow. All right. Let's go purple. So we have V is equal to, we're integrating it from A. I'm calling this A here, so I don't have to rewrite that. I'm just being lazy. To 1 of A of x, which is this right here, dx. Okay, I'm going to throw this whole thing in my calculator because it's the only way to really do that. You can't find this antiderivative. Okay, impossible. Unless you know something I don't. Okay, here we go. Math 9. Okay, now one thing is we found that intersection point. So if I actually, oops, if I hit X, it's already stored in for A. So I'm going to, well, it's already stored in for X, but I'm going to store it in for A here. So that way I can do math 9, whoops, math 9, and I'm just going to put A here. If you don't put A there, you can just write that whole number down. I'm just being lazy. It's not lazy, it's smart, really. Okay, arctan of x +1, and that's quantity squared, dx, 2 point something. There you go, 2.498. And there you go.
Awesome.
Totally.
A value we can comprehend.
So that's basically the lesson for today. Any other questions on anything? I guess I should have screenshotted this. All right, if there's no questions, that's all I got.
All right.
Email me if you need anything.
We had lots of fun today.
All right, you too, man. Yeah, it was awesome.
Thanks.
Thank you.
Thank
Bye.
you, Mr. Ozarka.
Bye.
Goodbye.
Bye.